All right, welcome to our next chapter, which is going to be chapter 6. And in chapter 6, what we're going to do is kind of fly through some terms and some parts of triangles that are going to come into play a little bit later in the semester. So it just kind of sets some groundwork for some of our later topics. We're going to start with the first section today, which is, again, just going to kind of be some vocabulary, a couple theorems that we're going to then take and apply in some of the future sections for this chapter. So we start off here, like I said, with just some vocabulary, and it's not really new vocabulary. We've seen perpendicular bisector before, so this is more kind of just review of some of these ideas and what we're dealing with. So for a perpendicular bisector, it's a line that's perpendicular, and so we know it's perpendicular when we see that little box in the corner. It means that's a right angle. So it says line PC here is perpendicular to line segment AB. So those two pieces are perpendicular because of that little box in the corner. The other thing a perpendicular bisector does, remember, bisect means cut in half. So we're going to hit the segment at the midpoint, which means this distance from A to P is going to be the same as the distance from P to B. So those two pieces of information, when we talk about perpendicular bisector, we're saying these two pieces of information must be true. The lines are perpendicular, they form the right angle, and we cut one of the lines in half. So A to B is cut into half from A to P and P to B. The other vocabulary term that we're going to see used pretty commonly throughout the chapter is the idea of equidistant. So we have the term right here, equidistant, and it just means that they're the same distance from each figure. So point P here is equidistant from point A and point B. So you're going to see that term used a lot. It just means it's the same distance away from two other objects. Now with this perpendicular bisector, the theorem that goes along with perpendicular bisectors here says that if a point, so if any point lies on the perpendicular bisector, then it's equidistant from the endpoints. So what we're talking about here in the picture to kind of illustrate this, we see that line PC. So here's line PC. It's perpendicular, and it cuts this line segment AB in half. Those two pieces of information have to be there. So it's perpendicular and it cuts it in half. What we're saying then is any point on that red line that I've highlighted, so point C particularly, is going to be the same distance away from each point on the segment. So C to A is going to be the exact same distance as C to B. And with this perpendicular bisector theorem, it's any point on that perpendicular bisector. So if I put another point down here, call it point D would be the same distance from B as it is from A. So these two pieces here, if I were to connect, would be the exact same distance away. So anything on that perpendicular bisector is going to be the same distance away from that line segment. And again, it's got to be the perpendicular and the midpoint markings there to make this work. Now on the flip side of that, we have the converse, because it can actually work the other way as well. And so with this converse, what we're saying is if we start with a point, so point D down here, and we see that point D is equidistant from A and B, meaning that it's the same distance from A as it is from B. Now what they're saying with this converse is if I know that information first, so DA and DB are the same, then this point D falls on my perpendicular bisector. So if I look up here, I've got the perpendicular and then the bisect markings there. And so what's going to happen is point D has to be there. So this perpendicular bisector theorem works both directions. Knowing it's a perpendicular bisector means we're going to be equidistant. If we're equidistant, then we're on the perpendicular bisector. So it's going to work either direction. And how this works, we can illustrate that with a couple of examples here. So if we look at these three examples, example number 1 here on the left, when we look at this picture, the things that we're looking for, the pieces that kind of hint as to what we're dealing with, I see that the line BD is perpendicular to line segment AC. I see that right angle there. And I also see that AB and BC are marked congruent. So I know B is the same distance away from A and C. Now, because these two things are here, it tells us that BD is a perpendicular bisector. And so what that means is any point on there is the same distance away from A and C. So when I see point D out here, point D to point A is going to be the exact same distance as point C to point D. So when they ask for line or the distance from C to D here, A to D is 27, C to D must also be 27. And that's because of that perpendicular bisector theorem. Okay. In example number 2, we have almost the same type of information. So we see that line SQ is perpendicular to line PR. We got the little box symbol. And then this time, though, they're telling us that point S up here is the same distance away from P as it is from R. So this is the information we start with. Now from here, what that means then is that SQ is the perpendicular bisector for PR, meaning it bisects line segment PR, cuts it in half. So I've got these two pieces are identical. So if P to Q is 5, Q to R is 5. Well, so down here, when they ask for the distance from P to R, we can put those two pieces together, and P to R would have a total length of 10. And again, that's that perpendicular bisector theorem. In the third example on the right, so number 3 here, we see that we have a perpendicular bisector, so they're telling us those two pieces of information. What that tells us then is that point H is the same distance from E as it is from G. So anything on that perpendicular bisector is going to be the same distance away from the endpoints. So that means I can take the 3x minus 8 and set it equal to 2x. And then I can go ahead and solve that equation, and you guys can solve this, but you'd get x is equal to 8. So once I know what x is, it asks for the length of GH. So if I plug 8 into x up here, I've got 3 times 8 is 24. Minus 8 gives me a total distance of 16. So once we know what x is, we can plug it back in and figure out what's going on. So basically with this perpendicular bisector theorem, everything's equidistant from the endpoints. So all you got to do is figure out which pieces match up, set them equal, solve if you need to for x, and plug it in. Now the next thing we talk about is the angle bisector theorem, and this is almost the same exact thing as the perpendicular bisector. It's just a little bit different type of figure. So angle bisectors, remember, cut angles in half. That's what the bisect means. So when I look at the picture down here, what this theorem says is that if I have an angle bisector, so I see that those two angles are marked congruent. So AD is an angle bisector for the big angle BAC. What this theorem says is any point on that angle bisector, so specifically point D, is the same distance from this side of my angle as it is to this side of the angle. So if I have that angle bisector, if I have these two angles are congruent, when I follow them out to the sides out here, those two sides have to be identical to each other. Just like the perpendicular bisector theorem, we also have the converse. The statement also works in reverse. So if I'm looking at a picture with these angles here, I see point D is the same distance away from B as it is from C. So I see that these two things are identical. What that means is I can follow those back inside, and that means that this top angle BAD would have to be congruent to this bottom angle DAC. So it kind of works both directions. If the angles are congruent, the sides are congruent. If the sides are congruent, the angles are congruent. And so again, it works in either direction. So with our examples then, it's a lot like that perpendicular bisector. And so if we look at this first one, they want us to find the measure of angle ABC. So they want us to find the whole angle ABC, so that whole angle highlighted in blue. Notice in the picture, A to D and C to D are exactly the same, which means when I come inside here, the angles that are creating this also have to be the same. So this side must be 56 just like the other side. Well, so if I want the total angle ABC, I just take my two angles that I have and add them together. So 56 plus 56 would give me a total of 112 degrees. In the other figure, we start with the knowledge that these angles on the inside are congruent, which means when I follow those angles out, these two sides must be congruent. So the 4x on top has to equal the 2x plus 12, and then from there, I can go ahead and solve for x and then plug it back in to find Jm. So when I solve this equation for x, I get x is equal to 6. If I plug that back in up here, 4 times 6 gives me 24. So there's my distance from J to M. On the last example here, just kind of a word problem. It says a parachutist lands at point P, so we're landing right here on the field. If the parachutist wants to leave the field, it wants to go to the closest. So they got the third baseline over here versus the first baseline over here, and they're asking which one would be closer. Well, if we look closely at the picture, he landed right on the angle bisector. Those two angles are identical, which means his distance to first baseline and his distance to the third baseline would be identical. So either way he goes, he's going to go the same distance. With that information now, you should be able to go ahead and complete the 6.1 worksheet that you get in class or get off of Google Classroom. Make sure to check the answer key for that when it's available and ask any questions that you have either in class or email, whatever you might need to do there.